Hello, and welcome to Xamarin University, AND231 Location Services. Our goals today are to work with the GPS sensors on the Android devices and couple them with Google Maps, which we covered in AND230. We will look at two main things to get an overall picture. First, we'll explore how to retrieve the current location from Android using a standard built-in API, and then we'll explore how to find locations and display them on a map. Before we begin, let me tell you about the prerequisites for this course. This is an extension of the AND230 course, which goes into how to use Google Maps. Location is loosely tied to mapping. You can use it independently, but it is often used together in apps to show, and that's what we'll show today. As a result, you'll need the proper setup to use Google Maps, an API key from Google, and a device or emulator set up to run the Google APIs. Let's start by working with our current location. For some applications, knowing your user's location allows the application to provide better information to the user. It can be more relevant, tailored to where they are. In fact, if you look at some of the most popular social apps on the platform, Facebook, Twitter, Instagram, and others, all support location sensitivity to tag photos and status updates with your current location and provide some context. There are three things that we want to look at here. First, we'll look at how to request location updates from Android. As part of that, Android supports different ways to determine the location through the use of location providers. Some providers are more efficient and some more precise. We'll look at how to manage these location providers and work with different ones to get an accurate fix on our location. Finally, we'll talk about how to process location updates and balance the frequency and accuracy against the power usage our app will consume. To start with, let's quickly recap how we work with maps in Android through the built-in Google services. In AND230, we looked at using the Google Play service to render maps as fragments in our UI. This required a set of permissions in our application, a Google API key from the developer console, and a component to provide access to the Google API SDK. In that class, we used the mapping support to render interaction maps and show annotations on the map in the form of markers. We're going to continue on from that point, so we'll have a starting application which already has the mapping in place. We'll just need to set the proper API key. Remember as well that when we acquired an API key from the Google Developer Console, we retrieved our SHA-1 fingerprint from the debug key store and our app package ID to identify the application. We then added a metadata attribute to our assembly, which had the API key generated in the Google Developer Console. This uniquely identifies our application to Google, and without it, calls to the mapping service will be rejected. So now it's your turn to try out the Location Manager in your app. We're going to set up the Google Maps API key. Go ahead and open up the worksheet that you downloaded as part of the lab exercises for this class. And start with exercise 1. Just set up your Google Maps API key. You'll need that as we continue through the class. Pause this video and return when you're complete with that first exercise. Knowing where the user is allows your application to be smarter and deliver better information to the user. When developing a location-aware application for Android, you can use a variety of sensors to determine where you are. GPS tends to be the most accurate, but it only works outdoors, it quickly consumes battery power, and it requires time in order to get a location fix, which can delay your application's ability to display relevant data. Wi-Fi-based positioning can be used where GPS is unavailable. This approach takes advantage of the rapid growth of wireless access points by measuring the signal strength from all the wireless signals around the device and then correlating that back to several public Wi-Fi location databases. Depending on the area, this can provide a reasonable level of accuracy or be almost unusable. Or we can rely on cellular tower triangulation. This tends to be the least accurate because of the distance between towers, but in densely populated areas with good cellular coverage, it will give a general location fix. Android takes all of these approaches and integrates them into its Location API, allowing your device to get location information from a variety of sources and use that data to make decisions in your app. So let's explore that API. It all starts with the LocationManager service. This is the gateway into Android's location tracking capabilities. It provides a variety of features to your app. It allows discovery of available location providers, again GPS, cellular, Wi-Fi. It requests periodic or one-shot updates from one or more providers. You can set proximity alerts to be notified when the device enters into close proximity to a specified location. You can even provide mocked locations for a provider, which is useful in unit testing. Remember that the location service is independent from the maps. It's perfectly acceptable to use location services and not visualize the location at all. For example, you might query the current location to pass on to a weather service. To use the location manager, you must specify location permissions in the manifest. Both fine and coarse location are required. The location manager service is a singleton, and there's two ways to get access to it. First, you can use the standard GetSystemService call. Pass in the unique string representing the location manager, and that's the most common approach and is what you're going to find in the Android documentation. Second, you can call a static method on the location manager class itself. Pass your Android context and you can retrieve the location manager. This is a helper method that's provided by Xamarin Android, and it just forwards the call onto the GetSystemService approach. Once you have the location manager, you can select a provider and request updates from it. This is done through the RequestLocationUpdates method, which has several parameters. First, you must tell the location manager where you want the data to come from. This is called the location provider and is identified by simple strings. We'll explore that a bit more in the course. For now, we'll use the GPS provider, which is identified by a constant available on the location manager class. The location update interval can be controlled using the min time parameter. The elapsed time between location updates will never be less than the min time, although it can be more depending on the location provider implementation and the update interval requested by other applications. Choosing a sensible value for the min time is important to conserve battery life. Each location update requires power from the GPS, Wi-Fi, cell, and other radios. Try to select a min time value as high as possible while still providing a reasonable user experience so that you're not constantly requesting location updates. The min distance parameter can also be used to control the frequency of location updates. If it is greater than 0, then the location provider will only send your application an update when the location has changed by at least min distance meters and at least min time milliseconds have passed. However, it is more difficult for location providers to save power using the min distance parameter, so min time should be the primary tool for conserving battery life. Finally, location updates are received either by IlocationListener callbacks or by broadcast intents to a supplied pending intent. We'll be looking at the first approach as it tends to be more common. The second approach is useful when you want to receive location updates while the device is sleeping or when your application is not running. It involves creating a broadcast receiver. This is just a class that derives from broadcast receiver and creating a pending intent which maps to that receiver using the pending intent.getBroadcast method. When location changes occur, then location updates are sent with the key of key location changed and the new location value. Receiving location updates system-wide is not a common requirement. It's far more common to only want the updates when your application is running, so we'll focus on the callback method. Keep in mind that the callback approach can be used in the background as well as through the use of services, which we discuss in the backgrounding class. When using the LocationListener callback approach, you will often implement the callback directly on the activity that will use the location information. So let's look at the interface requirements. The LocationListener interface defines a callback which the location manager uses when the location is changed. The onLocation change method is passed the new location information when it changes and the minimum distance and time has elapsed. This interface also provides callbacks to let your application know about provider changes. Some providers can be turned on and off. For example, the user can disable active providers through the Quick Settings menu or through the Settings app. These provider methods allow your application to know when the providers are changing status and being enabled or disabled. We'll talk more about handling this a little bit later. Many applications don't care about this information, and if you fall into that category, you can just provide empty implementations. The onProvider disabled is called when the given provider, identified by the string parameter, is turned off. If you request location updates from a disabled provider, this method is called immediately in response. The onProvider enabled method is called when the given provider is enabled by the user or the device, and then onStatusChanging is called when the provider status is changing. For example, if the provider has recently become available after a period of unavailability. This can happen independently of the provider being enabled or disabled. GPS will report temporary unavailability when it loses a satellite fix, for example. When the location changes, you are passed a location data object, which contains a wealth of information, including the all-important coordinates expressed as latitude and longitude. These values will always be present in the location data object. Along with the position, you get other geographic data, such as direction, which is called the bearing, altitude, and speed. Most of this data is optional, as some providers can't reliably determine this information, so there's other properties indicating the validity of these pieces of data. The last two properties, provider and time, will also always be present, and they let you know which provider generated this packet, and a timestamp when the location was determined. This is a UTC time in milliseconds since January 1st, 1970. The location is passed to the onLocationChange method. If you're integrating it with Google Maps, then you can take the past coordinate, turn it into a lat_long object, and then animate the camera to that new position. This is just an example here. You would get the same effect directly from the built-in MyLocationEnabled property. However, if you wanted to represent the location graphically on the map in a different way than the built-in approach, this is the sort of code that you would use. There's three basic ways to test your location-sensitive code. First, of course, you can use a real device and go take it on a ride or walk about the neighborhood. This is the most real-world testing, and it's going to provide the best results. You should definitely always do this at some point. Second, as mentioned earlier, the Location Manager supports mocking out the location. You can do this through methods on the Location Manager itself, supplying a specific location to return for a provider. This can be used in unit tests to force a location to be reported for testing purposes, but for day-to-day testing, it's probably not what you want. Finally, most emulators support simulation of the location. The Google emulators can be influenced using the Android device monitor or from a telnet session. Alright, so you're going to go work again with the Location Manager. Go to your second exercise in the worksheet. Remember to pause this video and come back when that second exercise is completed. Android defines some standard location providers which are supplied on most devices, which we've already looked at: GPS, network, and passive. The GPS provider determines location using satellites. It's the most accurate, but it's only usable outdoors, and depending on conditions, this provider might take a while to return a location fix. This requires the permission Android.permissions access find location. The network provider determines location based on the availability of cell tower and Wi-Fi access points. The results are retrieved by means of a network lookup. This tends to be faster than GPS, and it works indoors, but it's less accurate. This requires either the course location or the find location permissions. And then the passive provider will provide you with location data when other apps that have requested location updates get their data. So if no other app on the phone is getting location updates, you won't get them either. This can be used when location isn't really central to your application and you don't want to incur the cost of activating it yourself. But if another application retrieves it, your app can get it too. This requires the access find location permission. Although if the GPS is not enabled, this provider might only return course fixes. Now, the manufacturer is responsible for actually implementing these providers based on the hardware and teleco systems available. And so the quality, the performance, and the accuracy of a given provider can vary from device to device. Additionally, both the manufacturer and the third-party applications can add custom providers to take advantage of proprietary hardware or custom mapping capabilities. Since these custom providers are custom and they're not available to every Android device, you'll have to discover them at runtime. This can be done using the Location Manager's All Providers property. This returns an enumerable list of strings that can identify all the providers installed on the device. The built-in providers all have known characteristics, which you can see here. One thing to be aware of when working with location is that providers can be turned on and off. That's why we have the provider methods in the IlocationListener interface. If you need to check a provider's state, you can use the Location Manager's isProviderEnabled method and pass in the provider name. This will return true or false based on the current enabled state of the provider. This isn't necessary in most cases though, as you can request location updates from a disabled provider. It just won't do anything until it's enabled, so you won't get any location change events. In addition, as I mentioned earlier, you will get a call to the onProviderDisabled method immediately if the provider is not available. Choosing the right provider can be challenging, particularly in the presence of custom providers created by OEMs. So the Location Manager has a method to help you select the correct provider based on criteria that you specify. You can specify the required accuracy, what features you need from the location reporting, and the power you're willing to consume, and then call GetBestProvider. This will return the provider string that you should use for location services. In addition, if you only want to consider the enabled providers, you can pass in true for the second parameter to the method. This will restrict the list to only the active providers. Another way to do this is to pass your criteria right into the RequestLocationUpdates method. This replaces the provider string and it selects the provider on your behalf. Remember that each location update passes you the provider that the location is coming from, and so you can tell which provider is generating the updates. Let's return to your worksheet now and go on to the next exercise. We're going to identify our provider based on some criteria. Remember to pause the video and return when you're done. Let's talk a little about application architecture when dealing with location services. Power usage is something that should always be on your mind. It's perfectly acceptable and expected for a mapping application to use GPS services with a high frequency update because users want to know where they are. It's understood that this will negatively impact battery life while the mapping application is active. And of course, I think you've experienced that. However, context-aware applications that integrate location to provide better user services, things like Twitter, need to be very sensitive to battery usage because continually tracking GPS location will drain the battery very quickly and will likely end up with the user dropping your app. So we have some guidelines to properly manage battery life. First, you can turn updates on and off at any time. When your application is in the background and not visible to the user, then you should either turn off updates altogether or at a minimum, switch to the passive provider and turn off updates from the active providers. That way, you continue to receive location updates at no cost based on other apps' usage of location. Once your app transitions back to the foreground, you can switch back to an active provider to receive more reliable updates. Alternatively, you can increase your update time to something fairly high, like every 5 minutes when in the background. When in the foreground, your update interval should reflect the importance of the location information. Shorter intervals when the information is critical to the application's data display, and longer when it's not. Keep in mind that the update time and distance values are really used as a hint to conserve power. The actual time between notifications might be greater or less than the supplied value, depending on other things happening on the device. So the first way to conserve battery is to only request location updates when you need them. You can turn location events on and off at any time in your application. To turn them off, you call the remove updates method on the location manager. Pass in the registered location listener. This will unregister the listener from all the providers you've tied it to. You should almost always turn off notifications when you receive the on-stop notification. That's your notification that the app is no longer in the foreground. We talk about the activity lifecycle and how to manage it in the Android 210 backgrounding class. Another thing to consider is, when do you need location data? In some cases, you might not need to know the device location until certain features have been activated or a screen is navigated to. In that case, you can defer turning on location services until that point is reached. If you don't care about accuracy, you just want a quick location position, or you need an immediate initial location to start with, you can query each provider for the last known location. This will return the cached location from the last successful read. This returns null if no location is available from the passed-in provider. So make sure to test it, as you can see here. Now, we've seen all the pieces. Let's put them together into a common workflow most applications will follow. Up to this point, we focused on using a single provider at a time, but to get a comprehensive picture of the location, you'll probably work with multiple providers together by making multiple calls to the request location updates, passing in the same listener. At some point after the application starts, it begins to listen to both the network and the GPS providers. It would retrieve the cached locations, comparing the timestamps to decide which one is newest, and then receive a notification about location changing from the network provider. This often happens first because GPS takes longer to get a fix. The app would then receive the GPS location and replace the Wi-Fi location with the more accurate location. Then the app might turn off location updates for some period of time so that the device can turn off GPS and conserve power. The app would keep the cached location, this is called the best estimate, for some period until it's considered stale, and then go through the same cycle again to refresh the location. This is just an example for most applications. Mapping applications would be different because they need constant updates. Most applications just need a periodic fix to support context awareness. And in fact, the passive provider might even be sufficient for that. First, we would retrieve the last known location from both providers and decide which one we want to start with. Remember that the provider might not have a last known location, so we need to test them for null first. And then, if both are non-null, we compare them based on the timestamp. We'll prefer the GPS version if they're equal. If we get a last location, then we store it off as our current location and run it through our normal location change logic by invoking the onLocationChange method. Next, we'll register with both the GPS and the network providers, passing the same IlocationListener handler so we receive notifications for both in the same place. At some point, we'll receive a new location from our providers. We'll want to compare it against the previous last known location. We'll start by checking the timestamp. Remember, this is a UTC timestamp of when the fix was taken, not the current clock time. Then we'll look at how accurate the data is. This is done by testing the accuracy property. This is reported in meters, how close the location is to our actual one. We can compare this against constant values or against our prior known location. We might want to take the time into account here as well. For example, we want to be more accurate, or the time of the last known location is more than 5 minutes out of date. We can check the provider and prefer one provider over another. For example, we often want to prefer GPS over the network provider. Then, once we've passed each condition, we would then store this off as our cached location to use within the app, and then update our UI to reflect this new location. We've already seen how we can work with location data using the Location Manager. Well, we have another option for devices that include the Google Play services. We're going to look at another optional location provider that can simplify managing and receiving location data for some devices. The Location Manager is the standard system-supplied way to get location services. However, if you're willing to take a dependency on Google Play services, there's an alternative called the Fused Location Provider. The Fused Location Provider analyzes the GPS, cellular, and Wi-Fi network location data in order to provide the highest accuracy data in a unified way. Also, this provider uses different device sensors to define if a user is walking, riding a bicycle, driving a car, or just standing in order to adjust the frequency of location updates. It simplifies the logic needed for apps to track the user's current location as you move indoors and back outside with improved accuracy and lower power usage. You can, of course, do all of this yourself, as we've just seen, but the Fused provider does all of this for you, allowing you to talk to a single provider rather than trying to manage the different providers on your own. It's included as part of the Google Play SDK, and therefore will not run if the device doesn't have Google Play services installed. So this won't work on handsets like the Amazon Fire. In addition, this API is only available for Android 2.2 and higher, so you won't be able to use it with the older operating system versions. In these cases, where it's not available, you'll need to decide what to do. You can fall back gracefully onto the Location Manager, prompt for a Play Store app update to get the latest APIs, or inform the user that the app can't run. In order to use the Fused Location Provider, you must have the Google API Services library component. This is available through NuGet. This will add the base support and the maps. The first step in using the Google Play Services Fused Provider is to request access to the Google API. This is done using a Google API client, which is created using a builder class. Google recommends you create this in your onCreate override. Notice that we first verify that Google Play Services is enabled. This is necessary because not all devices will support Google Play Services. If we don't support it, we can fall back on the Location Manager, which is always available. We specify some callbacks, specifically a connection callback and a connection failed callback. These are both interfaces which we'll look at in a moment. The important thing here is that you need access to the location services. This is what will enable the API from Google. In addition, you'll also need the fine and coarse location permissions in your manifest, just like with the Location Manager. Finally, we create the API client object through the build method. This must be the final call in the Fluent chain, and it returns a Google API client object, which you should store in a field. Once you've created the API connection, you must then connect it to the Google Play services. And this must be done before many of the Google Play services APIs can be used. Some methods will queue up on a disconnected Google API client, but most require an active connection. There are two methods involved, connect and disconnect. Connect is used to establish the connection to the API server, and it executes asynchronously. The result of the connection is reported through two callback interfaces passed into the API builder. Success through the connection callback, and failure through the connection failed listener. Once the application is finished using the client object, you must call disconnect to release the resources assigned to it. Google recommends following the pattern shown here in the code example. Call connect in your activity's onStart override, and then call disconnect in the onStop override. Notice that we're also testing it from null. This is because we will only initialize this if Google Play services are available on the device, as you saw on the last slide. Once you call connect, you'll get a callback indicating that the connection was successful or that it failed. The two callbacks are implemented as interfaces, typically on the activity which will use the API. The Google API client.iConnection callbacks is used to report when a connection is made to the API or when a connection is suspended. The onConnected method is called asynchronously after the connect request has been successfully completed. After this callback, the application can use the other methods exposed by the client. The connection hint parameter passed to the method contains specific data relevant to the services that we've requested access to when we create our Google API client. In the case of the location service, it will be null as no additional parameters are used. The onConnection suspended method is called when the client is temporarily in a disconnected state. This can happen if there's a problem with a remote service, like a crash or a resource problem that caused it to be killed by the system. You're passed the reason for the disconnection, and two reason codes are defined on the connection callbacks const class and in the documentation. When this method is called, all requests have been canceled and no outstanding listeners will be executed. The Google API client will automatically attempt to restore the connection. In response, applications should disable UI components that require the service and wait for a call to the onConnect to restore them. Finally, if the connection fails, you'll get a call to the onConnectionFailed method on the IOnConnectionFailedListener. This is past the connection result, indicating why the connection failed, no network, for example, or a sign-in required. The connection result class has a bunch of constant error values defined on it, which you can use to determine the cause. The onConnectionFailed callback is your opportunity to decide how to handle the failure. In some cases, all you can do is let the user know the service is unavailable, or use some other API instead. However, sometimes there's a recovery possibility by interacting with the user. For example, if the API you're trying to get to requires a Google account, you can prompt the user for their credentials. The way you do this is through the past connection result parameter. It will indicate the failure, which you can map up to integer constants on the class, and it includes a property named hasResolution that indicates whether the system can potentially recover through user interaction. If recovery is possible, you can call the startResolutionForResult to launch the UI. You pass an activity, which will receive the result code from the UI, and a unique request ID, which will be passed along with the result when the UI is dismissed. This actual launching intent is exposed by the connectionResult.Resolution property, and it can be used to take more control over the recovery process. Typically, as you can see here in this code, you'll make the current activity the receiver, and that means you'll need to implement the onActivity result. In the onActivity result handler, you need to check to make sure it's the request ID you expect, and then check the result code. If it's successful, then you need to reinitiate the connect operation. 2 more points on error recovery. Since this is an asynchronous UI that's displayed, it's possible that the UI could be up, and you get a second notification about connection failure before it's dismissed. You need to account for that by stopping reentrancy using a simple Boolean flag. Set it to true when you launch your UI, and reset it when the onActivity result is called, or if an error happens launching the UI. Speaking of errors launching the UI, make sure to catch the send intent exception, which indicates the UI was canceled. In this case, you can just start the reconnection process. Finally, once you're connected to the Google API client, you can use it to request location updates from the fused provider. This requires 3 things. First, you have to create a location request, which tells the provider what granularity you need and how to balance power versus accuracy. This is similar to the parameters you provide to the Location Manager when requesting location updates. You can see here that it's also a fluid API where we set values on it to establish the object data. Here, we're setting the update interval to 5 seconds, and the priority, which decides how to balance power. There are 3 values you can provide for priority: high accuracy, balance power, and no power. Generally speaking, the more accurate the location data, the more power you'll use. We then call the LocationServices Fused Location API static property, which exposes a set of methods similar to Location Manager. One of these is the RequestLocationUpdates. It takes the connected Google API client, the location request, and either a pending intent or an IlocationListener callback, similar to the Location Manager's implementation of this method. This will then begin reporting location changes through the fused provider to your callback or broadcast receiver. There is a catch though. The interface implementation passed into the fused location API is not the same as the Location Manager interface, even though they share the same name. They're defined in different namespaces. And that means you must implement both interfaces in order to fall back gracefully on the older Location Manager service. The new version of this interface defines one method, onLocationChanged, and luckily, or probably by design, it looks just like the older implementation. That means unless you have a need to differentiate, you can implement the onLocationChange method once and share that implementation for both interfaces. That's actually the default behavior in C# if you don't fully qualify the implementation. Now we're going to work on the next exercise. We're going to add support for the Google Location Services. Pause this video, open your worksheet, and continue on with this exercise, and then come back to this video. In this next objective, let's look at the geolocation address support built into the API. We'll use this API to locate points of interest on the map around a given location. Let's start with address lookup. Geocoding is the process of transforming a street address or other description of a location into a latitude and longitude coordinate. Google has full support to locate addresses and points of interest in the maps. You can use the built-in geocoder class and issue queries to Google servers and get back specific address information in the form of an address object. This API is completely separate from the mapping visualizations, and you can use it to look up points of interest, addresses, or general areas and then visualize it on a map, list view, or just use the information internally. The geocoder is our gateway to searching for things. It supports several variations, the first of which is to translate a coordinate into an address. This is referred to as reverse geocoding. Before we can do anything with geocoder, however, we need to make sure this API is available. Geocoder uses a background service to do its work asynchronously, and if that service is not running, or there's no network availability, then the API will fail. We can test this through the static isPresent flag on the geocoder class. Once we're confident that we have the geocode support, we can instantiate a new geocoder object, pass our context, and then use the location methods to find things around us. In this code here, we're using the getFromLocationAsync method to pass in a specific coordinate and get one or more street addresses from it. The number returned is based on the final parameter to the method. Google recommends a lower number to make the results come back more quickly. So here we just want the primary address at that coordinate. There are synchronous versions of this method as well, but you should always prefer the async versions because this is a web service call. The API returns a list of 0 or more address objects, up to the count requested. The address object is Google's representation of a specific postal address. It has a ton of possible details associated with it, including web addresses, phone numbers, street and city information, as well as possible landmark details. Depending on the coordinate, You might get quite a bit of information or little to no information. It really depends on how rural or urban the area is. Since different areas of the world store addresses differently, the address object manages addresses through an expandable array, which you can read using the getAddressLine method. A property, max address line index, tells you how many lines there are. So in this code example, we are combining them all together to retrieve the full address. Now we're going to continue with our next exercise, adding the geocoder to perform the reverse geocoding. Pause this video, come back when you're completed. We don't have to use coordinates. Geocoder also supports taking an address or location and get back the full address object for it through the getFromLocationNameAsync method. Again, notice that this is a task-based method that's asynchronous because it's a web service call. This works exactly like getFromLocation in that it takes the name and an expected return count. A variation of the method signature also allows us to specify a bounding box, a top left coordinate, and a bottom right coordinate. Results will be prioritized based on how close they are to the given box defined by the supplied corners. It's possible to see results outside the box, particularly if there aren't very many matches, but the order that they're returned in is indicative of how close they are. The Geocoder API is part of standard Android, and it should be available on most devices. However, Google does provide a Places API, which uses the Google Maps and Google database to provide more detail and a better set of search results, which can include more details like photos and descriptions. It also exposes an autocomplete API you can integrate in for local searches. You can see this in the Google Maps application as an example. Just like the Maps API, it requires an API key. However, it's exposed through a RESTful web service, which you can interact with using just HTTP client. And now we're going to go to our next exercise. We're going to use the geocoder and search for specific addresses by name. Pause the video and come back when you're done. Now before we end, let me tell you about two really cool lightning lectures we have available, which are related to this class. First, there's a lecture on adding geofencing to your applications. This is where you're notified when you enter into a specific area or leave a specific area. Apps can use geofencing to support location-based notifications. The second lecture shows how to use the Google Directions REST API to retrieve a route between 2 points and then draw it onto a Google map using the Shapes API. That lecture also has an example of how to mock out location providers. These lectures are available directly on the Xamarin University site, and they include sample code for you to explore. Thank you for watching this Xamarin University video on location services in Android.